Hello everyone. Let's continue our discussion on identifying reasons for crosstalk noise. Okay, so the next reason that we identified is the increase in number of metal layers resulting in increase in lateral capacitance. So to cut a long line into short, let's try to identify let's try to identify the definitions of each and every term in this line. Okay, so let's start with the capacitance part. Let me try to introduce you to different kinds of capacitance. Basically, two kinds of capacitance. So if you take a full-fledged chip and cut it from the center, you see something like this. It's a 3D. It's a cross-sectional view of the chip. So you have the substrate somewhere over here where you build the NMOS and PMOS transistors. On the top of substrate, you have an oxide layer. On that oxide you have the metal layer, which is the metal one for connections, for making connections. You have then again an oxide, you have metal 2, you again have some oxide, and so on. Okay, so there's a metal stack which is present over here. So the capacitance between two different metal layers is referred to as interlayer capacitance. The definition is quite obvious from the term itself. It says interlayer, which means the capacitance between two consecutive layers, that is referred to as interlayer capacitance. And the capacitance between two wires in the same level, in the same metal layer, that is referred to as lateral capacitance. So what we have said is the second reason for increase in crosstalk noise is increase in the lateral capacitance. And why the lateral capacitance is being increased? It's because the increase in metal layers. Now, why there is an increase in number of metal layers as we go to lower nodes? Let's try to understand that part now. Okay. So in 0.25 micron and above process, where we had been discussing this kind of chip, if you see this route, there is enough space available to accommodate more and more routes. Basically, we can add more and more cells over here. There is enough space available. It's all the routes were quite spacedly apart. Okay, if you consider this route is again very much spacely apart from this particular routes to adjacent routes. So if you see, there is a lot of space available for more and more routes to accommodate over here, but since it is not required, we are keeping these areas as free. So now in this case, the number of metal layers that would be required to get a connection, for example, from this point to this flop point, that will be very less. So a single metal layer with a single M1 metal layer, you can directly connect from this point to this point. With a single metal 2 layer, you can connect directly from this point to this point, and again use the same metal layer to connect from this point to this point. Okay, so this was the scenario a few years back. And also the width of the metal that you see, it's quite huge, and that actually helps in reducing the resistance. So higher the area, lower the resistance, R equal to rho L by A. So that was the reason of having a wider metal and having a single very few metal layers that will help us to enable this amount of connections. So as a result of that, as a result of the wider metals over here, if you see the overlap area between metal 1 and metal 2, this overlap area is pretty huge. In that case, this is referred to as interlayer capacitance, and that is pretty much dominant in a case where it was 0.5 micron and above process. Okay, so in a 0.5 micron and above process, the overlap capacitance across the layers across the consecutive metal layers, that was pretty huge, and that led into an increase in the interlayer capacitance. And that's why we say that in a process where it was 0.5 micron and above, the interlayer capacitance was dominant. Okay, so now let's move on to the next type, where we were looking into 0.1 micron and below process. So in a 0.1 micron and below process, as we explained in the videos, in the previous videos, this was the example that we were taking for consideration. So we had 9 instances of the same chip being deployed on the same area. So due to this, what happened, the number of standard cells got increased. So initially it was, let's say, 20, now it's 20 into 9. So number of standard cells got increased, the number of connections got increased. So each standard cell has to be connected to its adjacent standard cells, so that connections got increased, and as a result of that, the number of routes got increased. So now how do you accommodate that increase in number of routes in the same area? Previously it was possible because because the routes were very much spacely apart, but in this case the routes are not very the routes are placed very close to each other. So how do I take care of this thing? One is a simple solution. One simple solution that we can do is we can just reduce the width of the metals, but that is not enough. Even when you reduce the width of the metal, the num- the demand of routes in this area is too huge. So only reducing the number of bits won't help. So what we do is we do a connections in a different way. For example, if you see initially the metal one was directly connected, it was a straight line. But now what we are doing is we are taking the metal one, we are stopping over here, we are taking one connection on the next metal layer, which is, let's say, metal 2. We are continuing with the connection, we're again coming back down to metal 1, and then we're continuing with this connection. So now the signal which was traveling this way, it will now travel this way. So this happened because of the limited amount of resources, or because of the limited amount of routing resources available in this area. In the previous case, the amount of area that was available, that was pretty huge. In this case, the area has become very compact, and you have to accommodate, you have to connect signals at any cost. You have to do that, and at lower nodes. So basically at zero point 0.1 micron and below process, a single layer is being split up into two different layers. And this is just a small example that we have taken, and there are like billions of routes which are present on a chip. So in order to accommodate all these connections, all these routes, we have to make several this kind of connections at the metal 1 layer, or let's say even when we move to the higher metal layers, for example metal 2, if we don't find a space to continue this line, we have to again break this route in the center. We have to stack it, take it to the next metal, and again come back. So we have to do that. So that has actually resulted in increase in number of metal layers. Okay, so now we understand that there is an increase in the number of metal layers when we go in a process which is 0.1 micron and below process. So in this case, let's generalize this. So yeah, this is something like this. So number of metal layers compared to the previous has increased. Compared to the previous technology, it has increased. So now what you see is, first of that, there are two things that we observe when we go down to go down to zero point 0.1 micron and below process. The first thing, the width of the metal have reduced, okay, and the number of metal layers have increased. So this justifies increase in number of metal layers. Now moving on to the next part, which says that increasing number of metal layers resulting in increasing lateral capacitance. So if you closely observe over here, if you closely observe any of the metal area, these two parallel lines have got an huge overlap area among them. So that has resulted into a huge lateral capacitance between them. So initially there was a overlap area, there was a huge overlap area between two layers or between two consecutive layers. Now there is a huge overlap. Now this part is solved, this problem is solved. We no more have an overlap area between this metal layer and this metal layer, but we have an overlap area between these side walls. If you see this particular side wall, and if you see the side wall from that side, so there is a huge overlap area between these two, and that's the reason we see lateral capacitance dominant. And the biggest disadvantage we find with the lateral capacitance is that they're present on the same layer. Now if they are present on the same layer, any signal which is passing through this particular net will immediately couple to this particular net, because they are very close to each other. If you see, because of the congestion, if these routes are very close to each other, and as a result of this you see a coupling between these two nets. So any activity, any switching activity happening over here will immediately affect will immediately create an activity on this layer. We'll see how, we'll get into those details, but it's like it's like bringing two classrooms very close to each other. So initially we have taken the example of classroom A and classroom B. So initially classroom A was and classroom B were like a kilometer apart. Now they are few meters apart. So whatever is being taught in classroom A is being heard by students in classroom B, and whatever is being taught in classroom B is being heard by students in classroom A. So that's a pretty good analogy that we have it over here. So this is the second reason that we have behind the crosstalk noise, and the reason is the increase in the lateral capacitance. Okay, so let's move on to the third reason. It's lower supply voltage leading to lesser noise margin. So this will take a bit of theory lectures on this. So what we'll do is, since I'm already running out of time, let's try to continue and let's try to talk about this in the next video. Thank you.